Engineers build with signals that have corners in them. Clocks tick, pulses arrive and stop. Ones and zeros run past very fast. Almost none of it is smooth. An engineer who wants to analyze one of those signals draws a sine wave first. That happens with nearly every signal. In this video, I want to show you why. Nobody wanted the sine wave. A weight on a stick moves in its shape. You put it down, you let go, and it goes up and down like this. A pendulum does the same thing if the swing stays small. Push it far enough and the shape distorts. A coil and a capacitor do it too. That circuit has no moving parts. The two components pass electrical energy back and forth. All three do the same thing. Pull the weight down 1 centimeter and the spring pulls it back. Pull it 2 centimeters and the spring pulls twice as hard, still back toward the middle. That's what this equation says. And the minus sign is the back toward the middle part. Solve it and the motion you get is the sine wave. The second reason is about adding. A square wave jumps between two levels with no curve anywhere in it. You can still build one out of sine waves. A short pause breaks down the same way. So does a recording of someone speaking, and so does the radar chirp. Add the components back and you get the original. A perfect square needs infinitely many harmonics, but real signals are band limited, so a finite sum is enough. Adding sine waves is easy. Taking them apart is harder. Someone hands you a mixture. How do you find which frequencies are it? To find a 1 kHz tone, you correlate the signal with 1 kHz sine. Multiply the two and average. Matching frequencies give a real number. Everything else averages to 0. Do that error frequency and you get one number for each. Draw them as bars and you have a spectrum. Picture of what is inside the signal. The third reason needs a word first. Eigenfunction. An eigenfunction is an input to a system. The system rescales it without changing its shape. Take anything linear and time-invariant, a filter, an amplifier, a cable. Feed a sine in and sine comes out at same frequency, smaller, maybe bigger, and shifted. Amplitude and phase are the only things it may change. A square wave comes out of the same filter looking different, because its components are treated differently. Measurement depends on this. Put one frequency in, and whatever comes back sits at that frequency, so you always know what you are looking at. The generator supplies the drone and an analyzer reads that returns. Two numbers per frequency, the drop in amplitude and the shift in phase. Strip across the band and you have the frequency response. Most feed questions about the linear system reduce to something easy. Rating a plot. Communication uses the same curve. AM varies the carrier's amplitude, FM its frequency. Digital skims step instead of sweep. ASK, FSK, PSK, QAM. Two sine waves go into a mixer, which multiplies them. Two new sine waves come out, one at the sum of the frequencies, one at the difference. Radio fuse that to move a signal. And oscillator rings at one frequency. A comparator turns that ring into a squared colored edge. Along the bottom are the harmonics that add up to make the edge. The fundamental, then 3, 5, and 7 times it. So there are 4 reasons engineers keep coming back to sine wave. And here they are together. Nature, Fourier, linear systems, engineering. Nature oscillates in this shape. Fourier builds every other signal from it. Linear systems preserve it, so we can measure. Engineering carries and keeps time with it. Collapse all 4 together and one jar is left. Physics, mathematics, and engineering all ended up using the same shape. For watching. If this was useful, leave a like and subscribe for more.